What happens when an interviewer wants to truly test your algorithmic efficiency? Merge K-sorted lists is a Pattern Mastery 100 heavyweight and a frequent guest at Google, Amazon, and Microsoft interviews. Over 40% of candidates get slowed down by the complexity and pointer management. Master this, and you'll prove you can handle multi-list merges, priority queues, and advanced patterns. Let's attack Merge K-sorted lists with the basic problem-solving framework, a stepwise guide for turning chaos into clarity, even in the toughest coding rounds. Let's break it down. Given an array of K-linked lists, each sorted in ascending order, merge them all into one sorted linked list and return its head. Example: input 145, 134, 26. Output 1, 1, 2, 3, 4, 4, 5, 6. Real-world example: think about a system that needs to combine multiple log files, each sorted by timestamp, into a single unified log for analysis. A classic interview extension: how would you merge sorted streams from different servers in real time? Let's assess it. What's tricky here? Naive approach. Merge the lists one by one using the two-list merge logic, kilonewton, time, where n is total nodes, works, but not optimal. Optimal approach. Use a min heap, priority queue, to always pick the smallest head among the k-lists, giving you on log k time. Let's think step by step. Push the first node of each list into a min heap, keyed by node value. Repeatedly pop the smallest node from the heap, attach it to the merged list, and if there's a next node in that list, push it into the heap. Continue until the heap is empty. Let's dig deeper. Why a heap? It guarantees that at each step, you can efficiently, in O log k, get the smallest remaining node across all lists. Using a dummy node for the result list keeps the code clean and bug-free. Edge cases? Some lists may be empty. All lists empty? Output should be null. Here's the structure. Create a dummy head for the result list and a current pointer. Initialize a min heap and insert the first node of each list if not null. While the heap isn't empty, pop the node with the smallest value. Attach it to the current pointer. If the pop node has a next, push that next node into the heap. Move current forward. Return dummy.next. Now let's implement the min heap merging approach, pulling the smallest node across all lists at each step for an efficient combined list. We start by importing Python's heap module. This gives us a min heap, which is perfect for always pulling the smallest node next. Here we define our solution class, which will hold the merging method. This function will take a list of sorted linked lists and merge them into one sorted list. We create an empty list that will behave as our min heap. We iterate through each linked list. I is the list's index, node is the head of that list. If the current list isn't empty, we prepare to push its head node into the heap. We push a tuple containing the node's value, used for heap ordering. The list index prevents comparison errors. The node itself, so we can move along the list. This ensures the heap always knows which node is the smallest. We create a dummy node, a convenient placeholder so we don't worry about edge cases when building the final list. Tail will always point to the end of the merged list as we build it. While the heap has nodes, we keep pulling out the smallest one. We pop the smallest element from the heap. Node is the next smallest node among all lists. We attach this node to the growing output list, and we advance our tail pointer to this newly added node. If the node we just used has a next node in its original list, we push that next node into the heap. This ensures the heap always knows about the next available smallest element from each list. We return the node right after the dummy. That's the actual start of our merged, fully sorted list. And that's how this algorithm works. It first loads the smallest nodes from each list into a min heap, then repeatedly extracts the smallest and stitches the list together. Efficient, organized, and perfectly suited for merging many sorted lists. Let's check. These are three individually sorted linked lists. List 1, 145. List 2, 134. List 3, 26. Our goal is to merge them into one fully sorted list. With the min heap approach, we push the head of each non-empty list into a min heap, storing the value and a pointer to the node. Heap initially contains 1, from list 1, 1, from list 2, 2, from list 3, repeatedly pop the smallest node from the heap, attach it to the merged list, and then push that node's next into the heap, if it exists. Step by step. Pop 1, from list 1, merged, 1, push 4, next in list 1 pop 1, from list 2, merged, 1, 1, push 3. Pop 2, from list 3, merged 1, 1, 2, push 6. Pop 3 merged, 1, 1, 2, 3, push 4. Pop 4 merged, 1, 1, 2, 3, 4, push 5. Pop next 4 merged, 1, 1, 2, 3, 4, 4. Pop 5 merged, 1, 1, 2, 3, 4, 4, 5. Pop 6 merged, 1, 4, 4, 5, 6. No more nodes remain. And we've always taken the smallest available node at each step, so the final list is fully sorted. And that's exactly what our function produces. So, our implementation is correct. The min-heap strategy cleanly merges all k lists into a single sorted list while respecting the on log k, time-bound. Now let's implement the divide and conquer strategy, repeatedly merging pairs of lists to reduce the problem size and build the final sorted list. We're defining our solution class, which will hold the divide and conquer merging approach. This function receives a list of sorted linked lists and merges them into a single sorted list. We check if the input is empty. If there are no lists to merge, we simply return none. This helper merges 2 sorted linked lists into one sorted output. We create a dummy node to simplify handling the new merged list. Tail will mark the current end of the merged list as we build it. We continue merging as long as both lists still have nodes. If the node from list 1 is smaller, we attach it next. We connect the smaller node to our merged list and move forward in list 1. If list 2's node is smaller or equal, we do the same with list 2. We advance the merged list tail pointer so it always points to the last node we added. When one list runs out, we attach the rest of the other list, since it's already sorted. We return the head of the merged list, just after the dummy node. We start by merging lists in pairs, 1 apart, then 2 apart, then 4 apart, growing exponentially. We store the number of linked lists. While our merge interval is smaller than the number of lists, we keep merging them in gradually larger grouped pairs. We iterate through the list indices, merging pairs like 0 with 1, then 2 with 3, then 4 with 5, depending on the interval. We replace the first list in the pair with the result of merging it with its partner. We double the interval, because next round we merge the newly merged results together. After all rounds of merging, the very first list now contains the fully merged result. We return it. And that's how this algorithm works. It first sets up a helper that merges 2 sorted lists, then repeatedly merges pairs of lists using a divide and conquer pattern. Efficient, scalable, and elegant. Now we test the divide and conquer solution on an edge case, an empty list of lists. There are no linked lists to merge here, k equals 0. In the divide and conquer approach, we normally pair up lists and merge them 2 at a time. Repeat this process level by level, like merge sort, until only one list remains, but when lists itself is empty. There is no first list, no second list, and nothing to combine. The correct behavior is simply to return an empty result, i.e., null or, depending on representation. Our code should detect that lists is empty upfront, or naturally return null when there's nothing to process, and output an empty merged list. And that's exactly what our program returns, an empty list, which is correct for this input. So, our implementation is correct. The divide and conquer merge handles this edge case gracefully by returning an empty result when there are no lists to merge. When an interviewer wants proof you can scale cleanly, merge case sorted lists is the moment. Multiple streams, strict ordering, and no room for pointer chaos. This is where efficiency and clarity win. Let's do a recap. We're given k sorted linked lists and asked to combine them into one fully sorted list. Conceptually, it's like stitching together several already sorted timelines into a single, ordered sequence. We compared 2 paths, a straightforward pairwise merge that's simple but slows to 0 kN, and the optimal strategy, using a min-heap, priority queue, to always pick the smallest current node, achieving on log k. The heap approach keeps every step efficient and predictable. The plan: set up a dummy head and a running pointer, push the first node of each non-empty list into a min-heap, then repeatedly pop the smallest node to extend the result. Whenever we pop a node, we push its next neighbor, keeping the heap current until everything is merged. Handle edge cases like empty lists gracefully. We followed that blueprint exactly: dummy head for clean linking, heap for selection, steady pointer movement, and ran the solution on LeetCode without any errors. On the example 145.134.26, the heap produced the merged order 11234456. Additional cases, including empty inputs, passed as expected. The takeaway: when many sorted sources compete, let a priority queue arbitrate. It keeps your merge orderly, your complexity tight, and your implementation calm under pressure.